Welcome to the Explainer. Have you ever been driving down the highway, seen those massive wind turbines spinning, and wondered how they actually turn a simple breeze into the electricity that powers our lives? Well, today, we're going to break down the amazing science and engineering behind these giants.
Okay, so here's our game plan. We're going to start with the absolute basics, how we even begin to capture the wind's power. Then, we'll get our hands dirty, metaphorically of course, and do a full teardown of a turbine to see all its moving parts. After that, we'll look at why they face the direction they do. And finally, we'll zoom out and have an honest look at the good and the not so good when it comes to wind energy.
All right, first things first, let's get into the core concept here. This is all about taking something we can't even see, the motion of the wind, and turning it into something incredibly useful, electricity.
Now, before we get any deeper, we got to clear something up. People use the words windmill and wind turbine all the time as if they're the same thing, but they're not. A classic windmill, like you see here on the left, does mechanical work directly. Think grinding grain or pumping water. A modern wind turbine, on the right, has one job and one job only, taking that spin and making electricity. That's the key difference.
So when you boil it all down, a wind turbine is basically a giant energy swapping machine. It swaps the kinetic energy of the wind for electrical energy. But how do you know if it's doing a good job? How do you measure its performance? Well, engineers have this really cool tool for that, and it's called a power curve.
Check this out. This graph is basically a wind turbine's unique fingerprint. It shows you exactly how much power a turbine will kick out at any given wind speed. You've got wind speed along the bottom and the power it's generating going up the side. Every single turbine model has a curve just like this one.
And what's really cool is this curve shows you the three most important moments in a turbine's working life. First, you have the cut-in speed. That's the gentle little breeze that's just strong enough to get the blades moving and making power. Then, as the wind picks up, it hits its sweet spot, the braided output speed, where it's cranking out the maximum amount of electricity it was designed for. But if the wind gets too crazy, it hits the cutout speed, and the whole thing safely shuts down to avoid tearing itself apart. It's all about that balance between performance and safety.
All right, we've got the performance metrics down. Now for the fun part. Let's climb up that tower. Don't worry, we'll take the virtual elevator and see what's actually going on inside one of these machines.
It all starts with the tower. And yeah, its job is to hold everything up, obviously. But its height is a huge engineering decision. Why? Simple. The higher up you go, the faster and smoother the wind blows. Getting those blades way up high into that premium 5-star wind is absolutely key to making the most energy.
And now for the real stars of the show, the rotor blades. These are so much more than giant fan blades. They're incredible pieces of technology shaped just like an airplane wing. They use an aerodynamic principle called lift. As the wind flows over them, it creates a pressure difference that literally pulls the blade forward, causing that powerful rotation.
And what holds those incredible blades in place? That's the hub. Think of it as the super strong knuckle at the center of it all. It has to withstand unbelievable forces, and its job is to funnel all of that rotational energy from all three blades into one single point, the main shaft.
And sitting right at the very top, you'll find this big boxy thing called the nacelle. You can just think of this as the engine room. It's the protective house that keeps all the most important and most expensive parts, like the gearbox and the generator, safe from rain, snow, and sun.
Okay, inside that nacelle is where the real magic happens. So, the blades turn that main shaft really slowly, right? Only about 30 to 60 times a minute. That is way too slow to make useful electricity. So, that slow, powerful spin goes into a gearbox. This thing is an incredible speed multiplier. It takes that slow rotation and ramps it up to something crazy, like 1,500 rotations per minute, to drive the generator.
And that super fast spinning drives the grand finale, the generator. This is where the payoff happens. It takes all that spinning, all that mechanical energy, and through the wonders of electromagnetic induction, it turns it into clean electricity that can be sent out onto the grid.
So we've seen all the parts, we've taken the tour, but there's another really big design choice engineers have to make. Which way should the thing actually face the wind?
Pretty much every massive turbine you see today is what we call an upwind design. That means the rotor, the blades are in front, facing right into the wind. And there's a good reason for that. They get to catch that nice, clean, undisturbed wind. The other way to do it is a downwind design, where the blades are behind the tower. The question is just, do you want your blades to get hit by the wind before or after that wind gets all messed up and turbulent by the tower itself? Okay, so now we get how they work, inside and out. Let's step back and look at the big picture. What are the real-world benefits, and what are the challenges that we have to deal with when we use wind power?
On the plus side, the arguments are really, really strong. I mean, first, the fuel is the wind. It's totally free, and it's never going to run out. It's clean power, which is a huge deal. No greenhouse gases. And here's one you might not think about. Unlike a lot of old-school power plants, they don't need billions of gallons of water for cooling. That is a massive environmental win.
But you know, it's not all perfect. There are some serious challenges to solve. The biggest one, of course, is that the wind doesn't always blow when you need the power. You can't just flip a switch. Also, wind farms take up a ton of land, and they are very expensive to build in the first place. And then you have the local stuff to worry about, like the noise they make and the very real danger they can pose to birds and bats. So this all brings us to one final huge question. Now that we understand the tech and the trade-offs, what's the single most critical engineering puzzle we need to solve for the future of wind power? Is it building giant batteries to store energy for a calm day? Is it inventing new, lighter, stronger materials for the blades? Or is it finding a way for these giants to coexist more safely with the natural world around them? The answer to that is going to be a real game changer.